Section 10.7 on Taylor polynomials. Here are some examples of Taylor polynomials. We'll see soon enough where they come from. So what's going on? There are two sections left for us to discuss in Chapter 10, Sections 10.7 and 10.8. So some points that we want to think about right now. So in our last section, we spent a lot of time discussing power series. That was the point of the section. And so I hopefully you're able to be convinced of the how powerful, no pun intended, power series are. You can do lots of operations with them to you can differentiate them term by term, integrate them term by term. We saw a power series that was being used to estimate pi. Lots of interesting things that we can do with power series. And so the motivating question we're going to have in this section is, given a function, can you come up with a power series for it? And the thought that you should be thinking about is, we want a general approach. So what I mean by that is, if I ask you about this function, f of x is 1 over 1 minus 3x, of course you can come up with a Taylor series. Sorry, I shouldn't say Taylor series. We don't know what that is yet. I should just say you can come up with a power series for it by substituting in 3x into our well-known series for 1 over 1 minus x. But that's not going to help you with other series. So for example, if I were to talk about g of x is sine of x squared, how the heck do you go about finding a power series for this function? And so, actually, in this section and the next, we're going to be able to develop a method that will allow us to find a power series approximation that would apply even to something nasty like this. So the approach here in this section and the next, you should really think of sections 10.7 and 10.8 as kind of a unified whole. In previous editions of this textbook, the sections were combined into doing Taylor polynomials, Taylor series all in one shot. I think it's good that they are separated because this is such an important topic and we want to pay plenty of attention to them. But do you realize that this section and the next are really a unified whole? So how are we going to go about this? How are we going to go about our method for our approach for, I give you a function, you give me a power series for it? So the idea that we're going to work out in this section is going to be how to approximate functions with polynomials. So my question now to you is, have we done this before? And if I'm asking a leading question like that, the answer should be clear that it is yes. Have we ever approximated functions with polynomials before? And so the answer is yes, when we did linear approximation way back in Calculus 1. So what's going on there is, our basic idea was f of x is approximately equal to f of a plus f prime of a times x minus a. So if I can draw a picture here of what's going on, let's say that here is a function f of x, here is a, Here is f of a. So this is going to be, this was the L of s, the approximation is f of a plus f prime of a times x minus a. So we are approximating our function with a linear function. Close to a, we have a pretty good approximation. Further away from a, we have a worse approximation. So this is the genesis of our idea that we should be thinking about. Linear approximation. How do we approximate functions with linear polynomials? Well, guess what we're going to do right now? We're going to think about how do we approximate functions not just with linear polynomials, but maybe quadratic polynomials or higher degree polynomials. So let's, higher degree polynomials. What would happen if I were to ask you to draw, instead of a straight line approximation, a parabola that approximates f of x, and it does the best job of approximating f of x close to a here? And so that's what Taylor polynomials, let me not stumble over my words. That's what Taylor polynomials are going to do. They're going to be ways that we can approximate functions with polynomials of degree 2 or degree 3 or degree 4, whatever degree you want. And so in the next video, I'll give you the formal definition of Taylor polynomials and how to compute them exactly. But just to kind of finish off this intro, let me write down 3 functions for you. F of x is e to the x, g of x is 1 plus x, and h of x is 1 plus x squared over 2. And so these 3 functions all are going to be similar in some ways. Let me highlight the similarities between them. First, and the similarities are going to look at what happens when we plug in 0 into them. So f of 0, e to the 0 is 1. G of 0, 1 plus 0 is 1. H of 0, 1 plus 0 plus 0 is 1. So all 3 of these functions agree at 1. Sorry, at 0. Okay, let's calculate out their derivatives. F prime of x is e to the x. G prime of x is 1. H prime of x is 1 plus x. Okay, what happens when we plug in 0 into their derivatives? We get 1, we get 1, and we get 1. So these 3 functions, they all have the property, not only do they have the same function value at x is equal to 0, but they also all have the same first derivative at x is equal to 0. Well, they got the same first derivatives. Well, let's think about their second derivatives. F double prime of x, that's still e to the x. G double prime of x, that's 1. H double prime of x, that's, sorry, I made a mistake. The derivative of 1, of course, is 0. So what do we get when we plug in 0? We get 1, we get 0, and we get 1. So now there's a difference here. These 2 functions have different second derivatives at 0, but these 2 functions still have the same second derivative at 0. So as it turns out, if you crunch through all the details, easy calc 1 problem, g of x is the linear approximation to f of x, but h of x is the Taylor polynomial of degree 2 for f of x. Both of them, we are doing our approximation at x is equal to 0. So if I were to draw a graph of, here is e to the x. So this would be f of x. And so if I draw g of x, it would be the best straight line approximation. So that's g of x. And h of x would be a quadratic approximation that is even better. So that's what these Taylor polynomials are. They are polynomials that approximate our functions of whatever degree we want, a best linear approximation, best quadratic approximation, a best cubic approximation. We want polynomials of degree 3, and so on and so forth. And how we've what we mean by best whatever approximation has to do with checking that they agree to however many derivatives we want. So this function, this is the best linear approximation to e to x as x is equal to 0. It agrees at 0. Both the function and its first derivative agree at 0. This is the best quadratic approximation to f of x, and we see that because these two functions agree at 0, and their first and second derivatives also agree at 0. Okay, so that wraps up this intro video. In the next video, we'll give a formal definition of Taylor polynomials.